here, but the connection you'll see, I mean, the algorithm in some sense beats a lower bound that was proven via Fourier analytic techniques. And let me describe exactly, what is the lower bound and what is the upper bound. First of all, I'll mention my co-author. So this is work joined with Piotr Indyk, Huyen Nguyen, and Ilya Razenstein. Okay, so the problem I'm talking about is nearest neighbor search, which is, I hope many of you have seen it before. It's a basic geometric question. We think about it in high-dimensional spaces. So we have a set of points D. The purpose is to build a data structure on it so that given a new point query Q, we can very quickly report the closest point P. Okay, and the problem, just a quick slide on motivation. I know this might be the wrong query for this, but just bear with me. The nearest neighbor search appears, especially the high-dimensional version, appears in practice because the points usually model some kind of objects, for example, images, right? The images, can be, for example, these binary vectors, right? And the distance, for example, Hamming distance models some kind of dissimilarity between these images, right? And this is, nearest neighbor search will give you this K nearest neighbor rule, which is like one of the basic classifiers in machine learning. And because of that, it has a lot of applications for music recognition, bioinformatics, and whatnot. So very fundamental problem for high-dimensional geometry. And this distance, just to say that the points can come from different spaces, the distances can be different. So I'll talk here about Hamming in Euclidean, but this could be Euclidean, this could be eddy distance, earth mover distance, and other options. Why is this important in geometry? Also because this seems to be a very fundamental primitive that appears in many other problems. So, for example, if you want to solve the closest pair problem, you can solve it via this nearest neighbor search, or, for example, for some versions of clustering, and so forth. Okay, so this is the motivation for the problem. So getting to the algorithms. So this is the area where there is this notion, of course, of dimensionality. Things become very hard with higher dimension. So if you want to construct an algorithm, then there are essentially the exact algorithm. There are two extremes. One is to do, essentially full indexing, prepare for all possible queries, but then your space will be exponential in D, in particular n to power D. Or the other option is not to do anything, be lazy. And in this situation, there is no preprocessing. Space will be linear, but the query time will be linear as well, right? And in general, we'd like to combine these two, basically, linear space and query time, which will be, D, think of dimension as log n, let's say, right? So you want polylogarithmic query time, okay? Because of hardness of exact, there is a notion of approximate nearest neighbor search, and let me just define it quickly what it is. Even before I go to approximate, let me define a threshold version of nearest neighbor, where I don't ask the closest point, but I asked, given a threshold in advance, threshold R, think of it like scale, for example, I want any point within distance R. So pictorially, rather than giving the closest point, I might give either of these 2 points. This is a fine answer. And now C approximate, so let me define C approximate, is the following promise problem. Let's say I guarantee that there is nothing in this annulus, which is between R and CR, and I say that if there is something inside here, report me any point within distance CR. Okay, so put differently, if there is nothing in this yellow area, then I guarantee that there is nothing, and then you have to report the near neighbor. Okay. And the problem will be randomized, so we'll return point P with 90% probability. Okay. With approximate algorithms, there have been a number of works since decades now. So let me talk about one particular direction for algorithms. This is called locality-sensitive hashing, and think about locality-sensitive hashing as a randomized space partitions. Okay, maybe this will be more familiar to you. So what we build here, so how do we do this kind of algorithms? We partition the space using some hash function, which maps, for example, so this is for Euclidean space, but you can think about also Hamming, from RD to some universe, some integer universe, such that for any 2 points, First of all, we partition, we'll have a guarantee, which is kind of has two parts. And one part says something about close points, means within distance r. So this is, the distance of our close point to the near neighbor, positive answer. And far is everybody else. This is kind of the false near neighbor, right? The points we do not want to report. And what do we want from this partitioning? We want this partitioning such that the probability that points collide when they are close is high, and the probability that they collide when the points are far is small. So just to make sure, how many people have seen locality-sensitive hashing before? Okay, cool. So a fair number. Okay, so I'll go quicker then. So this is how roughly it would look like, and how to construct, so this is a random hash function, how to construct such a data structure for a nearest neighbor data structure. You just partition, you hash into a table, and when a query comes, you go into the bucket where it falls into, and you look for the points here. And if this is really like this, high is say 1 and small is 0, then we'll find exactly our near neighbor in the bucket, right? So now I probably know that this is not really possible to have such a big contrast between high and small. So usually what is obtainable that this probability is not so small, this probability is small, and you have a particular gap with which you play. Just pictorially, you'll have a hash function which partitions the space such that the probability of collision drops somehow with the distance. And the faster it drops, the better we get algorithms. And in particular, once we get something of this sort, we will not use just one hash table, because one hash table we might not find the near neighbor. So we'll have to do several hash tables, basically pick several space partitions, and we hope that at least in one space partition we find the near neighbor. And the number of hash tables is specified by this parameter rho. So it is n to power rho. Rho is subunitary, so less than 1. And just to define how rho looks like, so let me define probabilities P1 and P2. So P1 is this probability that we collide when the distance is r. P2 is probability that we collide when the distance is CR. And rho is such that this inequality holds, right? So think of this as, we want to set P2 roughly to be 1 over n, and then P1 becomes something like 1 over n to power rho. So this is how many times we'll repeat. Okay, so this is this is the approach, right? I mean, now I shall tell you kind of, we need to construct these random hash functions that achieve interesting growths, right? And so this is what was proposed in original Indik Motwani paper. Okay, I should say that, we can define actually this function g as a concatenation of primitive functions. The notion of rho remains exactly the same. This allows us to do some boosting. And just to do LSH, just to give an example, so how to do such a random partitioning in Hamming space, well, just define coordinate cut, right? This is just pick a random coordinate cut, this will give you space partitioning, right? So formally, this will be pick a random j, your hash function will be a projection on coordinate j. And you can compute exactly what are these probabilities. So it decreases, goes down with the distance between P and Q, and you can compute exactly what it is, doing some approximations. You plug in the formulas, you get 1 over c. Okay, so as long as the approximation is bigger than 1, you get sublinear query time. Okay, so this is roughly how it goes, right? So what do we know? So let me kind of have a table with kind of what people what is known about this, and let me kind of partition this by L1 and L2 because the results are slightly different, even though they're directly related, because of the embeddings. So the original paper proved rho equals to 1 over c, and by the standard embedding of L2 into L1, this also transfers to Euclidean space as well. So later work. In later work, we showed that in Euclidean space you can get rho roughly 1 over c squared. And so this is the case. And in meanwhile, people have started thinking about lower bounds. So you have a space partition, and you can think about can we prove a lower bound, saying that this is the best space partition you can get. And indeed, the first time Motwani, Nauer, and Panigrahi showed that rho has to be essentially more than half divided by c, 0.5 by c. At least for high enough approximation. So this is the regime I'll think about. And later on, O'Donnell, Wu, and Zhu showed that rho has to be at least 1 over c. So essentially showing that this is tight, okay? And again, just because we can put Hamming into L2 squared. Okay, so the same holds for L2 squared. There are also results for cell-probe lower bounds. So this is by Panigrahi, Talvaro, and Dider, which essentially show that if you want space less than this, and this is kind of a trade-off, then you need super constant number of memory lookups, cell probes. Okay, so if I won't go into cell probes lower bounds, but this is what I want to point out, that for locality-sensitive hashing, for these space partitions, for this definition of take hash function partition the space, what is this contrast? This is tight, right? This rho, say 1 over c, and here is 1 over c squared. 1 over c squared is tight. Okay, so LSH is tight, and is the only thing left here to prove tight cell probe lower bounds? Is that all? Apparently no. So this is our main result, where we show that we can actually get nearest neighbor search in say Euclidean in Hamming space with rho which is 7/8 by c, essentially, at least for high enough c. Okay. So this, the lower bound was 1 over c, right? So this is improving by constant, the exponent. And this is, first improvement over original locality-sensitive hashing for Hamming space. And actually, we obtain this result via showing nearest neighbor search in Euclidean space, where we get, the equivalent. Basically, rho is equal to 7/8 divided by c squared, at least for high enough c. And this also improves upon our previous paper with Piotr. Okay, so these are the results, and probably the interesting part that I should really explain here in the talk is why is it possible to go around the lower bound, right? So for that, I will. So this is the algorithm that I want to focus on, this regime, because this will imply also result here. And how does it go? So let us look at the LSH lower bounds. Roughly, how are they proved? So the lower bounds are proved in Hamming space because these also imply in the lower bounds in the Euclidean space. So they are usually Fourier analytic. And let's say the original setting of Antoine or Panigrahi roughly should like this. So I won't show you the details, but roughly kind of what is the setting, what do you have to prove. So you pick any distribution over hash functions, so the space partitions. So you define P2 to be this probability of collision of random P and Q in the Hamming space. P1 is probability of collision between P and Q, which is essentially noised P, right? So we add the right amount of noise so that the gap of the distance is exactly C. And okay, and with some smart work, you get rho is at least half divided by C. Okay, so then the question was, okay, can we get better, right? And a few years later, O'Donnell, Wu, and Zhu showed that yes, we can get tight rho, and essentially these are modifications in the setting. The proof is different. I should say, there is much more work, but this is the difference. So basically, rather than looking at the distance between random pair versus P and Q, which are correlated at something, we correlate P and Q in the both setting, and this is correlation noise epsilon, and this is a noise epsilon by C. Okay, and in this setting, you can get rho is at least 1 over C. Okay. So the question is, okay, so, why isn't this not a nearest neighbor search lower bound? So this is not a nearest neighbor search lower bound because this kind of distribution doesn't lead to a good distribution when we have endpoints. So when we have endpoints, basically what do we need to do? We need to pick a point called Q, and then we need to take a lot of false near neighbors, many points which are far away, but they all need to be correlated with Q because this is the distribution, right? So now that you have a lot of points that are correlated with Q, this means that there is a small ball that contains all of them, and if you think about it, then the near neighbor has to be roughly close to the center of that ball. So kind of if you look at the data at the beginning, even before the query comes, you already see some structure in the data. So this structure can be exploited. So this is the message, right? You can ask, like, well, can we prove rho equals to 1 over C in the distance regime half versus 1 half by C? where this problem doesn't appear? So the answer is no. So actually in this regime, even the original kind of coordinate cut will give you a rho which is roughly this, of this form, 0.72 by C. So you cannot prove such a lower bound. And in fact, even though this was not done for nearest neighbor, but for a, essentially closely related problem, which is the offline problem, the closest pair problem, where the times are something like n to power 1 plus rho. So in 2010, Dubiner showed this kind of lower bound, which kind of suggests a rho of, that looks like a half by C. So yeah, again, think of C as being sufficiently large. So actually, at least, and this is for random data, okay? So random data, and maybe, so there is a lot of random data, and maybe one pair is correlated, so, so that we have a gap of a distance, okay? So this later was improved by Greg Valiant for this case to truly subcubic algorithm, truly subquadratic algorithm, actually, using other methods. Okay, so so this is the intuition, kind of, right? Why the lower bound is not necessarily a lower bound for nearest neighbor search. Okay, so how do we, how does the algorithm proceed? So I'll give you a high-level overview of the algorithm. So the idea is to do data-dependent locality-sensitive hashing. So think about this. So originally, what we did, say, random coordinate cut, or for Euclidean space, you do this ball carving procedure, if you know what I'm talking about. But the space partitioning was independent of the actual data. So you would argue only about pairs of points. So here, the idea is to say that let's look at the data, at the endpoints that we have, and let's do space partitions, still random space partitions, but that do depend on the data. Okay? So there are two components, kind of, roughly speaking. One is to identify a particular geometric configuration of points where we really obtain rho which is less than 1 over c squared. So it will be kind of, ideally it will be something like half divided by c squared. And then there will be a reduction from the general case to this case. Okay, and okay, each of these steps will, at least the idea will be just one slide. Okay, so assume we have the following setting. So all the points are on a sphere. Okay, the sphere doesn't show up. Are on a sphere of radius CR divided by root 2. So let me, yeah. So this is the sphere. So the radius is CR by root 2. So CR, think of it as like CR is the distance between, far pair. Why CR by root 2? Because if you take two random points on such high-dimensional sphere, then the points will be roughly a distance CR. So essentially, it kind of simulates this random situation for Hamming space where one could get rho better than what was the lower bound. So in this situation, one can obtain rho which is half divided by c squared, and proof. Okay, it's just a picture, not a proof, I guess. But this can be obtained by what looks like cap carving. So pictorially, you draw some random lines that cut parts of the caps of the sphere. This will be one bucket. You do it several times. This will be another bucket, and do so forth, right? So basically, each new line carves out the other part that still remains, right? And basically, each of these parts, will define a bucket. So this is somewhat similar to ball carving that was originally done for some rounding and by Kargim Motwani Sudan, and we also used with Petrendik for obtaining this tight locality-sensitive hashing for Euclidean space. So in this setting, at least, it turns out that rho that you obtain is better. You obtain half divided by c squared. So, in the interest of time, I won't be able to explain why. But in general, if radius, this kind of improvement over the lower bound is possible even when the radius is slightly more than CR. So if it is more by some eta, think of like 10, then you still obtain something that is better. It depends on eta, right? It decays with eta, right? Something has to decay with something because we cannot obtain better than 1 over c squared in general. So this is kind of this special configuration where we can obtain beta rho. And in general, the idea is to, the reduction is to apply a few rounds of regular locally sensitive hashing, something like ball carving, and then apply this spherical LSH. So intuitively, what happens is that so we can apply this data independent partitioning that will partition space a bit and will make the far points unlikely to collide. So basically, it reduces to the case where the points are more clustered. So if you set up the parameters right, then this partitions the data into buckets of diameter which is roughly proportional to order CR. So think of this as eta CR. Then you find the minimum closing ball in each bucket, and on each of these minimum closing ball, you apply this spherical locality-sensitive hashing. Okay, so just pictorially, kind of to describe the algorithm, how it looks like. So we again will have essentially n to power rho hash tables, each with a hash function, but hash function will not be just a concatenation of data independent hash functions, however many there was needed. Now we'll have a prefix will be some space partitioning which is data independent, and essentially kind of constructs some kind of structure or exhibits some kind of structure from our data. And after that, after we kind of reduced the data to some more structure, we apply the spherical LSH, which gives us better exponent. So in general, this ball carving will look like balls that are just carved out of a space. Perhaps something like this. This is this part, this data independent part, and then you look in each of the bucket. You look where the data. You draw some balls around them, and then you do this spherical LSH, which carves out cups. Right? And that's roughly the algorithm. Modulo many details. This is white lies, right? But here are some of the details. So the idea is that what happens in the end is that there are this is why we call it two-level hashing, is that there is the first level is data independent, and in some sense, as long as we are doing this data independent thing, we cannot obtain beta rho. So we'll still obtain 1 over c squared. But the hope is that the first level will make pairs at distance tau c, so tau is some parameter, unlikely to collide, which means that we will effectively reduce to the situation where in each bucket after this first level, we will have balls of small radius, of some kind of small radius. And in level 2, once we have small radius, we find minimum closing ball. We can actually find balls of radius tau c divided by root 2. And this uses this very nice theorem, Young's theorem, which says that diameter tau c, if there is a point set of diameter tau c, you can find minimum closing ball of radius tau c by root 2. And this is roughly how the analysis says, and then it will be kind of two parts, right? There is her part which loses, basically doesn't have any improvement on rho, but improves on the structure of the data, and the second part does the beta rho, right? And there are some more details in the algorithm that we need to drop off some pairs that are further than distance tau c, because there will still be some, unfortunately. We'd like to find approximate minimum closing ball just because this is faster. So you find balls. What I described was spherical LSH. So one has to take this ball. You take some shells there and approximate them and run on each one separately. But this is the general kind of overview. And that's more or less it. Just final slide, just to repeat what I said. So what we are proposing here is a new nearest neighbor search with which obtains exponent rho, which is for n to power rho query time, obtains rho, which is 7/8 by c squared for L2 and 7/8 by c for L1, which curiously goes below the lower bound that have been proven previously for locality-sensitive hashing, and really the idea is to look at data-dependent space partitions, right? So space partitions that do look at what actual points we care about. And of course, the natural questions remaining are, can we get better upper bound? For example, first natural idea is to think about multi-level, and this does improve a bit the constant, but definitely doesn't go, all the way down. That, might be considered a natural barrier, which is half by c squared. This is roughly because the Motwani and Navarpani-Grahi proved lower bound of this sort for L2, and that might imply a nearest neighbor search lower bound. We don't know. Or maybe not. Maybe one can prove something like a data-dependent lower bound. Right? That would be an interesting possibility.
Or like a distribution for nearest neighbor.
Right. So you look at. So you don't. When you do the space partitioning, you don't know the query. Okay. So this is the deal. Right. So you look at your points. You have endpoints, right? You don't know where the query comes into. You have to partition your space into some parts so that, comes the query and you have these probabilities P1, P2, and, you have this gap, right? This is what it would mean. So your function H kind of will depend on the endpoints for which you need to argue, right? Right.
So that, in some sense, is a...
Yeah, but this is, okay, so this is a cell probe lower bound, right? And the problem there is mostly that the type of lower bounds that you get is your query time is something like omega t, right? So you want, just because of the state of the lower bounds in cell probes is around log n, kind of, right? We don't have any more, especially, any higher lower bounds for static data structures, especially. And so, proving a lower bound of a sort of n to power something is still far away for any problem, right?
But if you're allowed to partition, can't you just use the Bornai cells?
So there is the question of, let me think. Good point. I guess, it has to be with more conditions, yeah. Question?
How does the problem change if the data is dynamically changing? If the set of points is dynamically changing?
So this is for static data structure. Yes, we haven't thought about dynamic data structures. Original, so that was the very good part of the original locality-sensitive hashing, that it was data independent. So in some sense, it was very good for dynamic data structures. You didn't need to restructure space partitions. Here it does depend. So in case you have static data structures, it does give better algorithms. I don't know about whether this can be dynamized at the moment. Good question. Are there more questions?
Okay, thanks. Well, that concludes the official program for today. And tomorrow, let's see when we start tomorrow. Well, the first talk is at 9 tomorrow, so be here before then.